So one thing that we should note about relations and functions, more specifically functions, is a special set known as the image set, which is the collection of all elements B, such that B is, we denote f of A to be the element that A maps to under the function B, such that the element A is an A. All right. So functions need not be assigned, by the way, to all elements of a codomain. If I have, let's say, 1, 2, 3, and elements 1 and 2, here's an example of a function. Notice element 3 here was not assigned anything, and that's okay. It's not required. This is what's called the codomain. The collection of elements here is what's called the image of the set A. And another fancy word that you might have come across is what's called the range. So this is the range, and this is the codomain, and this is the domain. Those are just some basics of the functions there. Now, there are three fundamental types of functions. The third being an extension of the other two. First, we have surjections. You might know these as being onto. A surjection is a function f such that, and by the way, we also write functions the same way we can write relations. We say a function f from the domain to the codomain. A function f is said to be surjective if for all elements in B there exists an element in A such that AB is in F. Put differently, if I have A and B, element, 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 a surjection is a function where I have every single element in B having an arrow coming into it, at least one arrow. That's a surjection. We then have the idea of injections. Okay, an injection is a function from A to B such that for all B1 and B2 in B, okay, if B1 does not equal B2 and there exists an A1 and an A2 such that B1 is equal to F of A1, that is A1 maps to B1, and B2 is equal to F of A2, A2 maps to B2. Then what we must have is A1 needs to be different than A2. Put very simplistically, if I have elements as such, okay, an injection is a function such that there's one and only one arrow coming into each and every, each element in B. Some elements don't need to have arrows going into, in which case it's not a surjection, but it could be an injection. You might know this as a 1-to-1 function. So put simply, surjection. If I take any element in my codomain, I can find an element in my domain that maps to that function. Or put differently, I can find an A in A such that the AB is in the set F. An injection is different. Injection is if for any two elements B that have arrows pointing to them, if those points are different, then the points from which they're originating must also be different. Okay, so that's injection, that is surjection. Last, we have bijection. Bijection is easy. A bijection is a function that is surjective and injective. Okay, so those are the basics of surjections, injections, and bijections. Very small example. Let's suppose we have the following 1, 2, 3, 4 for the set A, B, 1, 2. So you tell me, is this bijective, surjective, or injective, or none of them? Well, it is not injective because I have 2 arrows coming in here and 2 arrows coming in here. And in order for it to be injective, I need to only have 1 arrow coming in. It is surjective because for all elements in B, I do have an arrow coming in. It's not bijective because it's not injective. So therefore, this is only surjective. What about this one? It's the same sets, 1, 2, 3, 4, 1, 2. 3, 4, 5. 1, 2, 3, 4, 5. Tell me, injective, surjective, bijective? It's not surjective because 4 doesn't have any arrows pointing into it. It is injective because there's only 1 arrow pointing to the elements in B. So, and it's not bijective because it's not surjective. What about this one? 1, 2, 3, 1, 2, 3. This is a function, but it is neither injective nor is it surjective. It's not surjective because 3 doesn't have an arrow. It's not injective because 2 has 2 arrows going into it. Now, last, what about this? What if I do this, this? This is surjective because each element has an arrow going into it. It is injective because each element has only 1 arrow going into it, and therefore it is bijective. Now, you might notice that there's an interesting relationship here between bijectiveness and the number of elements in each set. Think about it. Isn't that interesting?